In this talk, I'm going to be giving an overview of a compact visual syntax for Haskell as part of the Glance project, whose goal is to make visual programming languages scale to large programs and large systems. So the goal of this is to make a system, a tool, that enables everyone to compute. And one of the existing tools for this is our visual programming languages and visual programming environments. But so far, these have been limited to specific domains such as music or video games or test equipment. And I want to make a tool that enables, like a general purpose programming, textual programming language, enables anyone to make, to do anything with the computer. But currently the issue with visual programming languages is that they don't scale, they aren't able to represent complex code or complex systems. The goal of the Glance project is to see whether we can go past that barrier and make a general purpose visual programming language. And so I believe one of the key things that we need in order to solve that problem is a compact and easy to read visual representation of code. In the Glance project so far, I've done some experiments with visually representing Haskell, which I think are on the right track, but is not quite there yet. So in this talk, I'm going to present a more compact visual syntax for Haskell, which will be sort of in addition to Glance's existing more graphical representation. And then the plan is, after getting feedback and input, to implement a visual editor for a subset of Haskell, where the inputs and the outputs of the editor are textual Haskell files, and then use this visual editor to create large programs and large computing systems. And if this is successful, then it should be evidence that visual programming languages can scale to large general purpose computing problems. So there's one key idea underlying the design of the new compact syntax, and that's there's no barriers between the different sort of programming representations we already have. So already we have graphical, we have structural editors, we have textual code, but really these are all points along a continuum in a space of designs of representations of programming languages. And so Glance sort of merges and is sort of a point in between these other representations. So I'm going to give a quick overview of the visual syntax and then follow that up with a more in-depth presentation. So at its core, Glance is a node and wire based representation. So here are all the nodes representing the syntax. Let's start with applying a function. Then we can define a function. We can have if-else statements, or in Haskell this would be a multi-if or a guard. Here's a do notation, which can represent, among other things, sort of sequences of actions. And here's a case in which we're doing pattern matching. And then node syntax, by default, there's just a wire that connects two nodes. But sometimes if a wire would clutter things up, we can make the wire invisible with a tunnel. Or instead of a wire, we could have a funnel so that way wires that go in front of tunnels, there doesn't have to be a line crossing there. Multiple wires can be grouped together into a bundle. And then the bundle can be used directly in a function application, or the individual elements of the bundle can be extracted. Bundles can also spawn child bundles. So this copies all of the values from the parent bundle into the child bundle. But then new values that get added to the child stay in the child. They do not get added to the parent. And this is a way to represent lexical scope. Now for a few examples, here's fizzbuzz. So here's the main expression we're traversing, and we're mapping a function over a list. And so this is the function we're defining. It takes an argument x, and it has this big multi-if. to check whether x mod 15 is equal 0 or x mod 3 is 0, etc. And then if so, fizzbuzz or fizz or buzz. And if none of them, then x, just show x. Here's factorial. We're just defining a function here. Again, we have a multi-if. If x is greater than 0, then we go to this recursive case where we're doing x times the factorial of x minus 1. And then if x is not greater than 0, we just return 1. And so you can see here we're using tunnels, and the value of the function itself can be got at by connecting a wire to the lambda. So that's how you can do recursion. And then this is an example using a case. This is just some code from the old Glance library. And so the core idea, is that textual, structured, and graphical representations are but points along a continuum. So to illustrate that, we'll start with a very graphical representation where each node is separate, and then we can slowly collapse nodes into each other. And we can go from a sort of a more graphical, free-form layout to one that uses indentation. We start using the tunnels, make things compact. And then we can sort of, remove the wires, add names for variables, and get a more structured feel for it. And then we can go from the structured representation and make it a bit more textual. And so now we've gone all the way from graphical code all the way to textual code as a series of continuous changes. So if you'd like to get involved, I welcome all feedback. You can email me, make bugs on GitHub, and stick around if you'd like to see a more in-depth presentation of the syntax and a little bit of how this syntax enables scaling to large programs. So there are a few sort of general strategies. One is to make the syntax more compact, is to overlap nodes and embed nodes in each other. Another, to eliminate lines and crossings, is to use indentation-based grouping, which means you don't need as much sort of visual stuff to show the relationships between things, since that can instead be represented using indentation. And then just a goal of this was to make it similar to the textual Haskell syntax, because for the editor, I imagine in practice you'll be going between the visual and the textual syntax, like for version control. And so you want to make that, easy. So let's start with function application. It's basically Lisp style. Instead of parentheses, it's a box. And you can do multiple arguments. You could also sort of rotate the application 90 degrees. This is just to sort of make layout nicer. To define a function, you have this trapezoid with the lambda on the left and then the argument list on the right. And then the result gets put into this trapezoid on the bottom. And so both this trapezoid here, sort of the boundary and the boundary of this trapezoid here, represent the function itself. And then what's inside here is the return value of the function. And so for identity, you could even just sort of put the return value right in there. Use indentation, so the body of the function is in between sort of the opening trapezoid and the closing trapezoid, but indented a little bit. Here's an example of 3 arguments. The arguments are in parallelograms. Parallelograms are patterns, and so they sort of fit nicely into this trapezoid when you sort of cut off a triangle for the lambda. And then names are their own box. They're sort of optional in most cases. Here's a function. So we've defined a function, compose, which has function composition. And now here we're going to use it in a function application as the function and apply it to 2 arguments. And here's just an example of how you can sort of compactify things. we've done composition and then we actually given an argument. And now this is just going through how sort of the reduction steps. So we copy the arguments into the parameters and then we do the reduction. Here's a case expression. There's an opening symbol, a closing symbol, and then in between are pattern matches. And then inside of the opening symbol, you can put an expression. So here we're doing f of right 3, and then this gets matched with left. That fails, so then it gets matched with right. And then the result is represented with this square. So y is going to equal 3 in this case. And then this is just showing a more compact layout for this. Here's a comparison of sort of the equivalent text, and you can sort of compare the compactness. Ifs, or in Haskell guards, or more accurately multi-ifs, since multi-ifs are expressions. These are sort of opened with a triangle, and then the booleans are connected to these circles, which are half white, half black, to represent a boolean, sort of, and can be in either one of two states. And then the result is connected to a star. The symbols here are fairly arbitrary. In an implementation, these sorts of symbols are fairly easy to change. And this, triangle can either go on the top or the bottom, and then this is the result. So here we're comparing to see if 4 is greater than 3. It is. And so we return the string greater than 3, so that's what comparison string will be equal to. If instead this value was 2, then it would be 2, we'd evaluate this Boolean. This Boolean would be true, and we'd get less than 7. And as like with functions, we can directly use the result of an if inside of an expression directly below it. So here we're concatenating 4 is plus this string here. Now, do notation. This more or less follows the textual notation. So we sort of have an opening symbol, a closing symbol, and then you can connect to these. These are sort of the overall expression, and then just a linear sequence of monadic expressions. And then the values you get from the monadic expressions on the right, you can extract out on the left, and then use them. So now the wire syntax. The colors of wires are pretty much random. In Glance, they're just sort of assigned arbitrarily. Just tries to make them different colors so you can distinguish the different wires from each other. So a tunnel, you have one triangle, and then there's sort of an invisible wire to the second triangle. And then these triangles can be, it's a random color, but it should have good contrast with the color of the wire it's connecting. And then there's this extra sort of trapezoidal bit of that color, just so you can sort of, you see X, and then you see this big green section, and then you can sort of skip over to this big green line, just to help things out. Here's an example. And then sort of here's an example of using tunneling with an if, so we can get values sort of directly in to these expressions here. Another sort of syntactic sugar for lines is what I call a funnel. And so the problem here is that if your sort of sub-expression is, really close to your expression, then you're going to sort of get, this line in like 1, 2, 3 extra line crossings, which doesn't look great. So instead we can sort of use a foreground background effect and just sort of draw this triangle sort of that looks like that goes behind all the other wires, and then you don't get as strong a line crossing. And then another little trick is, let's say you have a wire that, sort of goes all over the place, makes a whole bunch of turns. It can be sort of hard to follow. And so the idea here is that on one end, you have a little directional arrow which points to the other end of the wire. So here we're pointing to 2, here we're pointing to the 4, to the 3, to the 1. And you can have potentially multiple signposts per node if it connects to multiple things. So here's an example sort of with that other funnel example. So we go directly from here to this string. Here's bundles. So we can group together, we have 3 wires all going from this lambda into this function application. And so we can group them together. So this symbol takes as input bundles or wires, and it produces a bundle. And bundles can be directly used as arguments to a function application. So it makes things really neat. And you can sort of just, put this symbol near a pattern, and it just sort of is assumed it'll pick up all of the nearby values from the pattern. There's just a few other sort of syntaxes for it. Here we're using a tunnel. Here's a signpost. And values can also be extracted from, individual values can be extracted from a bundle. So here, we get X, we get Y, we get Z. So this is sort of like the escape hatch from the visual programming. So here we're actually using textual identifiers. Now we get to child bundles. This is really a feature sort of created for more complex code where you're putting a whole bunch of stuff into bundles, and you have functions which have subfunctions, which have subfunctions, which means you have a whole bunch of different scopes. And so child bundles are a way to allow you to express these scopes. The way it works is that you have a parent bundle and you have this sort of copy symbol, which copies all the value from the parent bundle, and it creates a new child bundle. And then you can add values to the child bundle, and then these values will just stay in the child bundle, because it's like lexical scope. These values do not get added to the parent bundle. And sort of this syntax was chosen here because there's no line here, so it doesn't create an additional line crossing. Here's the FizzBuzz example again. Notice how it uses the tunnels, uses an if, and the if result is actually being used directly as the result of the lambda. So we just put it inside the lambda result, and then we put the lambda result directly inside this function application. So it's sort of like 3 layers of nesting here. And then just as comparison, here's the textual FizzBuzz. Now here's factorial. Again, the if result is getting put directly into the lambda, and then also we're using this wire which connects to the outside of the lambda, and this is the lambda itself. So that's how you do recursion. And just sort of to make things nicer, this has a lambda here. It could also just be a white circle. And then this is an example I just pulled from the existing glance code. So here we have sort of an outer function and then an inner function. And then in this function, we take this function's parameter and pass it directly into a case expression. And so we're matching this against, it's a maybe. And then if it's a just, then we take its parameter, apply a function to it, and that becomes a result. So notice here we're using a tunnel, and we're also using the name. The name is optional. And then here's an example of using a funnel, sort of to get this as name, since it's real close. It allows the expression to be put right underneath the pattern, saving space there. The inner function is, getting used right here. Again, we're using a tunnel with a name. And then here's a signpost. So you can see okay, this case result comes from over here. And then here's the textual code comparison. Okay, so what about large functions? The answer is we cheat and use essentially textual references. But it's, it's a continuum, so if things are close together, you can use a visual connection, and then if they're far apart, then you can use a more textual connection. And the way we use textual names is by using bundles, because to get a value out of a bundle, you can use its name. And we also use child bundles, to which essentially mirror the lexical scope of the variables. So here's just some code from Pandoc, and it's just sort of annotated, where values would get added to a bundle, and then where child bundles would be created. And then the idea is that sort of each individual section here could be represented visually. Okay, so now you've seen the syntax. Let's go back to sort of the coding continuum, and you can see how we go from a graphical representation, and then we're sort of moving towards this compact glance representation. So this is the factorial function we've seen before, and then we can sort of go beyond that, get rid of the wires, and go from structural to textual, etc. Here's the example from glance I saw before. And to actually develop this more compact representation, I sort of took the code and then sort of did ASCII art around it to add in the various bundles and wires and things. And then, I posted BizBuzz to this Future of Coding Slack group, which is great. And a bunch of people had comments and suggestions. So here's a slide sort of incorporating some of the feedback. And then the next step is to do a full visual editor for Haskell. I guess the idea of Haskell is that it's a general purpose programming language. Being a pure functional language, it matches well with just sort of a graphical node-based representation. The editor will also produce textual Haskell files, so that way you don't have to replace all of your other tool chain. And so it reduces the scope of the project to just the visual representation. And please get involved. You can send me an email with feedback, or if you're just interested, want to talk about visual programming languages, etc., please reach out. If I'll be, sort of working on the visual editor, if that sounds interesting at all, then I welcome, all contributions. If you want to pair program, if you don't know Haskell, that's fine. And then if you want to have, I guess, more in-depth feedback, or sort of want to share your feedback with a little bit of a wider audience, then you can make a bug on the GitHub. Doesn't need to be bug, could be about anything. And specifically, the next step is a Haskell GUI, Haskell visual editor. So any advice about Haskell GUIs, which one to use, things to watch out for, would be very much appreciated.